Next, I'd like to introduce the reshoot logic, including pseudo-CMOS and DCVSL, differential cascade voltage switch logic. The reshoot logic, I will give you a review of reshoot logic. So still remember, I told you that in my previous lecture. So the logic levels are not dependent upon the relative device size, so that transistors can be minimum size. And also transition from one state to the other does not depend on relative device size. That is the definition of reshoot logic. And I also still remember I gave you this example, right? And I told you that this is a clocked RS flip-flop. And in this case, we have to cautiously design the size of the M8, M7, compared with the size of M4. Therefore, we can guarantee the pull-down network should be stronger than the pull-up network. Then the function of this one could be correct. Okay. So this is actually a reshoot logic. So in terms of complementary CMOS, the robustness, reshoot logic, full logic swing, high noise margins, symmetrical VTC, and no static power consumption, ignoring transient effects during gate switching. And the number of transistors required to implement an input logic gate is 2 times n, right? Because we have NMOS transistors in pull-down network and n PMOS transistors in pull-up network. Therefore, the area and total capacitance are relatively large. However, if we design the reshoot logic rather than reshootless logic, we have some good things. The objective to reduce the number of transistors required to implement a given logic function. Therefore, we can reduce the area, silicon area, right? Reduce the cost. The approach is to we can have NMOS transistor pull-down network that realizes the logic function, and a simple load device implementing the pull-up function. Okay, and the good thing that it can reduce the number of transistors from 2 times n to n plus 1, because we have NMOS transistors in pull-down network and 1 transistor serving as the load device. So that totally we have n plus 1 transistors. In terms of complementary CMOS, we have n NMOS transistors in pull-down network, and we have another n PMOS transistors in pull-up network. Okay, so reduce the number of transistors from 2 times n to n plus 1. The bad thing is that it can reduce the robustness and give rise to extra power dissipation. I gave you the symbol of the reshoot logic. In this case, we have PMOS transistor serving as the load device, and with the input of PMOS transistor is connected to ground. And this is a pull-down network. Same issue here, we can have another one. We have resistor here. Resistor here serves as the load device, and we have the same pull-down network here. So this is called pseudo-CMOS. This is called resistive load. So our goal is to reduce the number of the devices over complementary CMOS. This is a basic property of pseudo-CMOS. We have n plus 1 transistors, then VOH, the output voltage, high output voltage equals VDD, power supply. The nominal low output voltage is not equal to 0. That is because, this is expression for the output voltage low equals VDD times this one. So the output voltage low depends on the resistive divider composed of the pull-down network and load device. So VOL equals VDD times RPDN over RL plus RPDN. Therefore, because the VOL is not equal to 0, it decreases noise margins and increases extra static power dissipation. Sizing of the load device relative to the pull-down devices can be used to trade off between parameters such as noise margin and power delay and power dissipation. I can give you an example. In this case, noise margin low, it needs large resistance, RL, right? Because if this is large, if RL is large, then the VOL goes to 0, right? VOL is low. So in terms of noise margin low, we need large resistance, load resistance. However, in terms of performance, for example, TPLH, we need small resistance. Therefore, TPLH is small because TPLH equals 0.69 times RL times CL. So to decrease this one, we should decrease the resistance. So we have to trade off between these different parameters. Okay, so how could we solve for the output voltage low VOL? We assume that the CMOS resides in linear region, while PMOS transistor is velocity saturated. Then we can equate the current through the load device as well as the pull-down network. So this is the current through the pull-down network composed of CMOS transistors. This is a current through the load device, the PMOS transistor. This is velocity saturated. This is in linear mode. So assume that the VOL is smaller than VGT. VGT here is a shorthand of VGS minus VT. And we assume that the VTN equals VTP in absolute value. Then we can derive the VOL equals this one. Mu P times WP over mu N times WN times VT set P. Okay? And in order to make VOL as small as possible, the PMOS device should be sized much smaller, which can make the PMOS device weaker and weaker, right? Much smaller than the CMOS pull-down device. However, this has negative impact on program delay TPLH, so we know that before, right? And also we have static power consumption in the low output mode because the VOL is not equal to 0. Therefore, we have current. We have current when VOL is low, defined as I low equals this one. Then power consumption equals VDD times I low, approximately equals VDD times this one. Okay, so that's the case. So even though the circuit does not change, we still have power consumption. So that's a big issue for the pseudo CMOS logic. So you would better take into account, in some case, the effect of channelless modulation effect. And this folio tells us, so we have, you can see this picture. This is a V in, this is a V out, okay? If the transistor of the PMOS transistor is small, therefore it could be successfully put down, okay? Otherwise, if the pull-up network, the PMOS transistor, is strong with bigger size, therefore it's harder for the pull-up network to pull it down, okay? So you can find out when size of this one, PMOS transistor equals 4, equals 2, equals 1, and this is equal to 0.5, 0.25. Maybe you will ask that how could we implement transistor with W over L less than 1? So in this case, we can actually increase the length of the PMOS transistor. It is not equal to 0.25. We can increase the length of the PMOS transistor. Therefore, we can construct a PMOS transistor with the size W over L less than 1. Now, I'd like to give you my first problem in this lecture. So given the choice between NOR and NAND, so which one do you prefer for implementation in pseudo CMOS logic? So you know that in complementary logic gate, I said that the NAND is better than NOR because the logic effort of NAND is smaller than logic effort of NOR, right? Therefore, NAND is faster than NOR. However, here we have the pseudo CMOS logic. So which one do we prefer? So NOR gate or NAND gate? Give me your reason. That's the first problem. Then I'd like to introduce the DC-VSL. DC-VSL, differential cascade voltage switch logic. The objective of the pseudo-CMOS modification, completely eliminating the static currents, which means we don't want static current, right? The current from VDD to ground in static mode. That's the issue. And also can provide rail-to-rail swing and also reduce the TPLH. So how could we do that? If we can design a load called adaptive load, for example, if the output is meant to be high, then load current will be increased automatically. That's ideal, right? And the output is meant to be low, then load current tends to be reduced substantially or eliminated completely. That's a very good thing. So how could we achieve this? I can give you an example. So that's the introduction to the differential cascade voltage switch logic. So we have PDN1 here and PDN2 here. So when PDN1 is conducting, PDN2 is not conducting. Vice versa. PDN2 is conducting, and PDN1 is not conducting. Okay? And we have two load device, PMOS transistor here. This is out, this is out bar. Okay? If we assume the initial value of this one is the out equals 1, then out bar equals 0. Okay? And therefore, this pull-down network is not conducting. This is on. This is conducting. Because this is conducting, then out bar is connected to ground. Therefore, out bar equals 0. If out bar equals 0, then this transistor, M1, is turned on. Then out equals 1. Because this is off, right? So out equals 1. Okay, this is the initial case, initial state. If in some case, the PDN1 and PDN2 make transition at the same time. For example, this is turned on, this is turned off, right? Therefore, this is turned on, the pull-down network will try to decrease the voltage at out, right? Because the current will discharge the capacitor located between out and ground, okay? And you can find out at the same time, because out bar equals 0, then transistor M1 is still conducting, right? Therefore, transistor M1 tries to pull the voltage up. So they will compete with each other. If we can make sure that the pull-down network here is stronger than that of the pull-up network here, stronger than M1, therefore, the Vout will decrease a little bit, then turn on the transistor M2. Okay? If transistor M2 is turned on, then transistor M2 will try to charge the capacitance located between out bar and ground. Okay? Then the voltage potential here will increase accordingly. Then this one, in some case, will turn off transistor M1. Okay? If this one is turned off, then we don't have any current here, right? Then the out bar makes transition from 0 to 1, then out makes transition from 1 to 0. Okay? Then after this process, you can find out the DCVSL logic makes transition. Okay? So the structure of DCVSL, we have two pull-down networks. They are complementary and mutually exclusive, which means if this is off, that is on. This is on, that is off. Mutually exclusive. And static logic. So functions are implemented only by CMOS devices, possessing the same advantage of pseudo-CMOS logic, more suitable for the implementation of NOR logic, right? NOR logic because we don't want transistors in stack, in series. That's NAND logic. So in NOR logic, we want transistors in parallel. Okay? Be aware that careful PMOS transistor sizing is necessary to make the circuit function correctly. Okay? And differential logic. Signal and its complement are both needed, normally consuming more areas. However, if the two complementary pull-down networks can share some transistors, so PDN1 and PDN2 in some cases can share some transistors together, therefore area overhead could be alleviated substantially. For example, this one. In this case, we are going to implement exclusive OR as well as exclusive NOR. So exclusive OR and exclusive NOR can share some transistors. Therefore, can reduce the area penalty a lot. In terms of power consumption, so it consumes no static power, however, has power dissipation problem due to the crossover current. Crossover means the transition, the process of transition. And performance inferior to static complementary CMOS logic due to signal through effects. I will introduce later. So you can see here, we have DCVSL, transient response of the AND NAND gate. This is the AND NAND gate. So if we have the A and B mix transition at the same time from 0 to 1, then A bar and B bar mix transition from 1 to 0, then this is A and B, then this is A bar and B bar. You can find out then if this one A and B go up, then out will go down, right? Out will equals AB bar will go down. When the out go down, then it will have the out bar go up, okay? And here you can find out we have this one, that is because the signal feeds through. Therefore, we have undershoot first, then go up later. So in this case, the programming delay of the AND NAND gate equals 197 picosecond. Out bar equals this one. Compared with the complementary CMOS logic that is composed of NAND gate and inverter, the delay of that one is 200 picosecond. So this is because of the signal feeds through. Therefore, it is a little bit slower than that of the complementary CMOS implementation.